Okay. Hello, everyone. Welcome back for the last lecture. So I sent you 2 weeks ago an announcement on Toledo about the exam. Some people had questions because it was written that only handwritten materials were allowed, but I corrected it. What I meant is any paper material is allowed. So you can print the slides, you can write on the slides, you can bring notes. Anything on paper is allowed. Okay. Is there any other question related to the exam? Okay. So I also remind you that there is a mock exam online. You can attempt it and send it to me. The exam will happen through the platform ANTS. You can also try it out beforehand. I encourage you to try it out. And there will be on June 16 at 11 a.m. a Q&A session. So a few days before the exam. Does anyone have any question about what we did concerning chapter 5 last time? I will summarize it again, give you some reminders, but is there any question already? No? Okay, so we can just summarize what we did last time. So if you recall, on chapter 4, we discussed machine learning techniques for non-parametric models. So models that do not assume linearity in general, that allows for non-linearity. And in particular, we discussed the random forest as an example. Now we are, in this chapter, we saw how to adapt these techniques for causality and estimating and doing hypothesis testing on causal effects. And we studied several models. And the difference between these models and the linear models is that we relax linearity to some extent each time. We use these techniques, which like random forests, which do not assume linearity and allow to estimate functions which are not linear, to relax linearity in our causal models. So the first model we discussed was called the partially linear model. So it's a model similar to what we had in chapter 3, except that the effect of the control now is allowed to be nonlinear. Rather than having the control entering as xi transpose beta in the model, they now enter with a function g of x that is not assumed to be linear anymore. In this model, we still assume that the effect of d is the same for every x, and it's linear and it's equal to alpha. And what we want to estimate is alpha. So the difference with the model of chapter 3 is really that the effect of x is not constrained to be linear anymore. So to estimate this, a bit similar to what we did in chapter 3, we rely on a Frijol-Howell theorem for alpha. And this Frijol-Howell theorem says that in this model, alpha is the coefficient of the linear regression of EI on UI. And here EI is a part of Y that is not explained by X. And UI is a part of D that is not explained by X. If you recall in chapter 3, we had a similar result, but the model was fully linear. And then EI on UI were the parts of YI and DI that were not linearly explained by X. Here we drop the linearly part. We have the model is nonlinear in X, so the EI on UI need to be the part of YI on DI that are not explained by X at all. It's not only linearly, it's in general. Is that clear for everyone? Or is there any question on this? Yeah, okay, very good. So this suggests a natural estimator. We can estimate UI on EI by using the random forest of DI on XI and YI on XI and taking the residual of this random forest. You remember we saw in chapter 4 that the random forest allows you to estimate this type of models that we can call conditional expectation model. So they just here M of XI will just be the average value of DI given XI, and the random forest can estimate this. So we can estimate by random forest M on L. The residue then by we can estimate EI by yi minus L hat of xi, where L hat is the random forest estimate of L, and ui by di minus m hat of xi, and then alpha hat will just be the OLS estimator of the regression of EI on ui hat. Okay, so we are using this result here. The only problem with this result is that we don't know EI on ui, but we can estimate them using the random forest. This is exactly symmetric to what we did with the lasso, you remember, except that now M and L are not assumed to be linear anymore, so we can't estimate them by lasso, we estimate them by random forest. Now there was a little subtlety here, is that this perfect symmetric from the lasso did not work. So this is what you do if you do simulations. The red curve is a distribution of the estimator you should observe if you want hypothesis testing to be valid based on the last step OLS regression, and the blue is what you observe in the simulation. And that was because of a subtlety for which I tried to give some intuition, but essentially the idea is when you estimate M on L by random forest, the random forest overfits to some extent. So the estimator of the random forest is a bit too correlated with the error terms. And because of that, that creates bias in step 3. This doesn't happen for the lasso because the tuning parameters of the lasso is selected in a way that prevents this. But in general, it can happen with a machine learning algorithm. The lasso is an exception rather than the rule. So to avoid this problem, we use sample splitting, or more precisely cross-fitting. So the idea is to say, my problem is that my random forest will be too correlated with the error term. So what will I do? I will divide my sample in two. For instance, when I do 2 faults. On the first half of my sample, I will estimate M on L. Then on the second half of my sample, I will use this M on L to estimate EI as yi minus L at xi, and ui at as di minus m at xi, and then I obtain an OLS estimator of EI at on ui at. And actually, working like that solves the problem, because the overfitting problem is the fact that here, this estimator of the random forest will be correlated with the error term of the data, of this data. But when you split the samples, that's not a problem anymore, because the error term of this part of the data are not correlated with the error term of this part of the data. So it does not create a bias afterwards, because the overfitting here, in a sense, is independent from the error terms on this part of the data. When you don't split your sample, the overfitting, when you estimate the random forest, will have an effect on the OLS, because this overfitting is correlated with the error term of the data, which also affect the OLS in the second step. Is that clear for everyone or not? At least a bit of the intuition of why this solves the overfitting problem? Again, I can't give it's very technical, I can't give a full intuition, but at least I'm trying to explain it here. Now, of course, that's what we saw with cross-validation. When we do that, we don't use all of the data. Right? We only use a part of the data to do the random forest and another part to do the OLS. So to improve the precision of our estimator, what we can do rather than sample splitting is cross-fitting. You remember, like that's the same idea as cross-validation. Once we have done that, we reverse the role of the faults. We estimate then the random forest here, then do the OLS here, and we obtain a second estimator of alpha, and then we can average the two estimators. And the nice thing with this is the fact that then we will have used all the data at some point to train the random forest and all the data at some point to do the OLS. And this is what this algorithm does, except that here I propose to divide the data in capital K faults. This example is capital K equal 2. I divide the data in 2, but if you divide it in 5, then you have 5 estimators of alpha and you average them. Is there any question on this? Oh, very good. And here that works. So here you had an example. I'm going to skip it. And then we discussed an IV version of the model. So it's almost the same model, except that now we don't assume anymore that epsilon I is exogenous. So this is what we assumed before. Epsilon I, di was exogenous. We don't assume this anymore, but we suppose we have an IV Zi here such that the IV is exogenous. Okay, that's the standard IV assumption. That's exactly similar to what we did in chapter 3, and this model is exactly the same as chapter 3, except that now we allow the effect of x to be nonlinear. In chapter 3, we had the same model with g of xi assumed to be linear, and now it's not linear anymore. So to do the estimation, we can do again what we did before, almost exactly the same as we did with the lasso, except that now we will replace the lasso by a random forest, and we will do cross-fitting. If you remember, with the lasso, we also used a Frijol-Oval theorem, but for IVs. And this Frijol-Oval theorem for IVs was telling us that alpha is the coefficient of the 2SLS regression of EI on UI using VI as an instrument. Here, EI is a part of YI not explained by X. UI is a part of DI not explained by X, and ZI is a part of VI is a part of ZI not explained by X. The only difference with the chapter 3 on the lasso is that in the case of the lasso, again, that's the same. We assume that M, R, and L were linear, and then we could estimate them by lasso. And then the interpretation of EI, UI, VI was a bit different, because then there was a part of YI, DI, and ZI not linearly explained by X. Here we drop the linearly. That's the same thing as for the partially linear model. Any question on this, or is that clear? Okay, very good. And so what can we do? We do as before, we do cross-fitting to avoid this overfitting problem. And we estimate, so we divide the data in folds. On one fold, on the data not belonging to one particular fold, we estimate L, M, and R by a random forest. Then on the remaining fold, we estimate EI, UI, and VI as a residual of the random forest prediction of this new fold, and then we run 2 SLS on them. Okay, we obtain an estimator, we do that for all folds, and we average. Yes?
I was wondering, do you need to have control variables? You have many control variables. How do you determine which one are exogenous regressors in the IV framework?
Or do you determine which one? Okay. So essentially, you need, that's a very good question. Typically, one way to determine this is to put variables on which you have no ex ante choice. Okay, so this can be age, This can be genders, this can be parental education and these kind of things. And then the idea is more that, how can I explain? This is not, you have to see this as, here in this model, g of xi is not assumed to be the causal effect of x. So what matters here is when we say that x is exogenous, that's a bit of a different assumption than saying that di is exogenous. Because this is a model for the causal effect of di, and then here g of xi is just some kind of predictive effect of x. But we need to control for x to get the effect of di. So that's a bit of a complex thing to explain, but what you have to understand is that g of xi here is not assumed to be the effect of xi. So exogeneity for x doesn't mean the same thing as for d. Is that somewhat clear? I will need a few more, like a bit too much time to give details, but I think the main point here is to really say this is a model for the causal effect of di. Here we are not claiming that this is a causal effect of g. We don't need to assume it for this to work. We just need to assume that alpha is a causal effect of di. Yes?
Is this the same or is it different from the standard linear ToSLS framework?
That is also the same for the linear ToSLS framework. So you don't need to assume that the only thing is in the linear ToSLS framework, you kind of need to say that in the causal model for di, the predictive effect of x on y is linear. Okay, but this is really you need to think of this as a predictive thing. That's a very good question. Thank you. Okay, so now we know how to do that, and then we move to the interactive regression model last time. So in the interactive regression model, the idea was to relax further the assumptions, because in the partially linear model we still have this strong assumption that the effect of di is linear and it does not depend on x. It's just alpha for everyone. Okay? This is probably not a very realistic assumption. So if you think of the example of the effect of education on earnings, it might be that some people benefit much more from education than other people. So in that sense, it's not realistic to assume that the effect of di is linear and the same for everyone. So to relax this, we can consider the interactive regression model. This model only works in the case where your di is binary. So we write yi of d as a potential outcome under treatment d, where d belongs to 0 or to 1. An example of this can be, if you recall, in the problem set, you saw normally this coupon campaign, I think in the tutorial. So yi is a sales, and that you do to a customer in a shop, and yi1 is how much the customer buys if you give them a coupon. And yi0 is how much the customer buys if you don't give them a coupon. And what we are interested in that case is alpha, and alpha is the average treatment effect. yi1 minus yi0 is how much customer I would buy if they were given a coupon minus how much they would buy if they were not given a coupon. And then you average out over all your population. Okay, so we don't assume anymore that yi1 minus yi0 is constant and equal to alpha. This we don't assume it. Alpha this time is just the average of this. Okay? So in that case, in that example, we don't assume that the coupon has the same effect on every customer. We just assume that, we just define alpha as the average effect over all the customers. And then to estimate the causal effect in that case, we made several assumptions. The first one is the exogeneity assumption. So with the exogeneity assumption, we assume that yi1 and yi0 are independent of di given xi. Okay, so we say the coupon, when we fix xi, so xi can be age and, let's say, gender of customer, we assume that when you fix age and gender for given customer, the customers who are given the coupons are not different from the customer who are not given the coupon. And we also have to assume, of course, that when you fix xi, you have both customers that are given the coupon and customers that are not given the coupon. Otherwise, you can't estimate the causal effect, right? Because if you only have customers which are given the coupon, you have no idea what would have happened without the coupon and vice versa. Is that clear for everyone? Or is there any question here? Okay, so we have these assumptions. And what's interesting is that we saw last time that you can rewrite this model in this form, which is maybe a bit more intuitive for you because it relates to what we did in the previous section. This model can now be written as yi is equal to g of di xi plus epsilon I, where epsilon I is mean zero given di on xi. So you see it's similar to the partially linear model, except that now we don't assume that the effect of di is linear anymore. Di just can interact with xi in any way possible. And that's why we call it the interactive regression model, because there is an interaction between di and xi, which is possible. And last time, I will go quickly on that because we don't have the time, but last time we saw the different ways to estimate this model. One essentially is just to say, I fix xi, and then for a given value of xi, I compare the purchases of customers who got the coupon to the customers that didn't get the coupon. And then I average all of that over all the possible values of xi. That's one way. Because once I fixed xi, the customers that are given the coupon or are not given the coupon are representative of each other. The only difference is the coupon. So any difference in sales can only come from the coupon. The other idea is the propensity score weighting. This idea of this propensity score weighting is just, okay, if I were to naively compare the people in the population who are given a coupon and the people who are not given a coupon without conditioning on X, these are two different populations, right? Maybe we give the coupons much more to older people than others. Now, by assumption, if I can reweight these populations so that they have the same X, then they will be representative of each other in terms of having the coupon or not. Okay, so the idea is to say, this population, the ones who receive the coupon and the one who don't receive them, they have different X. But by assumption, if they add the same X, then they will be representative of each other. So I just reweight this population using this propensity score. And once I've reweighted this population, I can just compare the average purchases of the customers in the reweighted population that got the coupon minus the average purchases of customers in the population that didn't get the coupon. And that will identify the causal effect. Okay? Is that somewhat clear for everyone? Or not? Don't hesitate if there is any question. So these are the two methods. Now, for double machine learning, we will combine these two methods. If we were to use only one of the two, the estimator would not be asymptotically normal. It will not work for inference. So the way it works in that case is we will estimate G and M by an ML estimate and then combine them in another fault, and we will get an asymptotically normal estimator. So that's why the way the double ML works in that setting. In this model, we just combine two ways to estimate in the last step, alpha hat. Is there any question on this? I know I'm going quickly, but yes.
Is the first method more naive than the second one, or is
No, I mean, in general, there is no real preference between the two. What people prefer to do is to combine both of them like this. But these are two methods that, in principle, they will allow you to obtain an estimator that is consistent, meaning when you have a large sample, it will be close to the true alpha. But that estimator will not be asymptotically normal, so you can't use it to do hypothesis testing. You have to combine both of them to do hypothesis testing. And that's why we do that here. So don't try explaining why we combine them in that way is a bit complex. So don't try to understand the formula itself. Just understand that it's important to combine both of them. But it's very technical to explain where the formula comes from. Any other question on this? So this is what we did almost until last time. And we started very quickly on the IV part that we will finish today. And then we will do the very short last chapter on diff in diff, on difference in differences. So then we discussed the IV version of this model. And then you have some complications when you move to the IV version of this model that you don't see when you move from the partially linear model to the partially linear IV model. And this is here because this model allows for treatment effects which are not constant for everyone. So suppose we come back to our setting. We have a binary treatment. So let me give you an example. We will take again this 401k example that you saw in the tutorials. So the 401k it's a saving plan that your company can give you in the US. It's fiscally advantageous. And DI can just say individual I has a saving plan or not. We are interested in YI, which is how much they save. What is their wealth, essentially. And what we want to know is what is the causal effect of this saving plan on the wealth of people. So here, YI1 is how much individual I would have saved if they had a saving plan, and YI0 is how much they would have saved if they did not have a saving plan. Now, having a saving plan is probably endogenous, because to open a saving plan, you need two things. First, your company needs to offer it, and then you need to take the decision to do that. And this is probably endogenous, because if you don't care about saving, you're just not gonna open a saving plan. So you want to use an IV, and an example of IV here that we can consider is, does your company offer you or not to open a saving plan? ZI is equal to 1 if the company offers it, and ZI is equal to 0 if the company does not offer it. What's nice here is that compared to the treatment itself, it doesn't depend on your own decision. So it's more likely to be exogenous. Now, what's really important here is the idea of the IV is to say, essentially, if you remember, is to say, okay, I'm gonna compare the savings in the group of people who have ZI equal 1, meaning the group of people whose employer offers them the possibility to open a saving plan, and the group of people who have ZI is equal to 0. So meaning the group of people whose employer does not offer them to open the saving plan. under the IV assumption, these two groups are the same, except from the fact that they have access to the saving plan or not. So any difference between the two groups in savings can only be due to the effect of the saving plan. Now there is a key nuance here. The difference between these two groups will be that in one group, some people who are offered the access to a saving plan will accept this offer, open the plan, and save more because of it. But so the difference between the two groups can only be due to these people, these particular people who, if offered a saving plan, decide to open one. So in a sense, here we have no hope to identify the average treatment effect over everyone. By using the IV, we can only, in that case, identify the treatment effect on the people who, if offered a saving plan, would open one. The people who would never open a saving plan, we cannot identify the effect on them. This nuance did not matter before. Why didn't it matter before? Because we assumed that the treatment effect was the same for everyone. If the treatment effect is the same for everyone, the fact that we can only identify the treatment effect on this group of people doesn't matter, right? Because this group of people has the same treatment effect as everyone. Now in the interactive regression model, we allow that people react differently, that individual one reacts to having a saving plan by saving much more than individual two. Is there any question on this? Is that clear? Do not hesitate if it's not clear, if you would like me to repeat. Is clear? Okay. So what's interesting is that in general, in this framework, to understand what's happening, you can define 4 possible behaviors with respect to the IV. People can have 4 possible behaviors. One is never takers. These are people who will never take the treatment regardless of the value of the I. Then you have, so these are people, if you offer them or don't offer them saving plans, they will never anyway open one. Then you have always takers. These are people who have DI equal 1 regardless of ZI. Here they cannot exist because you cannot have DI equal 1 when ZI is equal to 0, right? You can't open a saving plans if you're not offered to. But in general, in this model, you can think in other applications that they might exist. Okay, but in this example of the pension plan, this one cannot exist, the always takers. Then you have the compliers. The compliers are people who have DI equals 0 when ZI equals 0 and DI equal 1 when ZI is equal to 1. So that means these are the people who offer, the people we are talking about, who if offer the pension plan, open one. And then you have the defiers. The defiers, they go against the IV. So DI is equal to 1 when ZI is equal to 0, and DI is equal to 0 when ZI is equal to 1. Here it's not possible, right? Because you can't have somebody who is not offered the pension plan that opens and vice versa. So in our particular application of the saving plans, always takers and defiers cannot exist. But in general, in this model, these are possibilities, right? One key observation is, so if you compare the groups such that ZI is equal to 1 and ZI is equal to 0, the difference between these two groups, right, in terms of savings can only come from the fact that by the IV assumption, once you have fixed X, can only come from the fact that different people have a saving plans in the different group. Okay, and what are these different people? They can only be compliers or defiers, right? Because these are the people who change their treatment choice based on the IV. So if I compare the group Zi is equal to 1 and the group Zi is equal to 0, once I have condition on X, of course, then the difference between these two groups in my population will just be that different people here have di is equal to 1 than here. Okay? And the difference can only be due to the defiers and the compliers. Because these are the people who change their behavior because of the IV. Now, there is this contribution of two Nobel Prize winners in economics. We essentially said, okay, let's assume that you have no defiers. That's our case in our application of the saving plan. You cannot have a defier, right? Because you cannot have somebody who opens a saving plan if they are not offered and does not open one if they are offered. That's by definition. Then the difference between these two groups can only be due to the compliers. So meaning, if I compare the average saving in that group and the average saving in that group, I will see a difference in saving, and this difference can only be due to the fact that the compliers here, they have the treatment, they open a pension plan, and here they don't. So essentially, what their theorem says is the following. If you assume the classical IV assumption, exogeneity, exclusion, and relevance, and what they call monotonicity, meaning there are no defiers, then you can identify the treatment effect, the average treatment effect on the compliers. And this average treatment effect on the compliers is what we call the late local average treatment effect. Here. Yes?
Why is there no assumption that there are no always takers?
Because what's important is the always takers, if they were there, they will always have the treatment in this group and in this group. So when you compare the average in this group and in this group, they cancel out. You see what I mean? Like they don't play any role in the difference between these two groups, because in both groups they have the pension plan or the saving plans. If they were always takers, of course, here we don't.
Then we need to assume that there are as many always takers in both.
Yes, and this is guaranteed by exogeneity, essentially, because people behave in the same way. So exogeneity just is saying, once you condition on X, the people in the group Zi is equal to 0 and Zi is equal to 1 are the same. Meaning we'll have the same proportion of always takers in both groups. We just don't want thing to show on the slide. So this is what we were talking about, the example of the 401k plan. And just to finish, so how can we estimate this late? So I hope now it's clear for everyone why this is what is identified in this model. Again, I just want to repeat that in the previous models, the late was equal to the average treatment effect, because we were assuming that the treatment effect is the same for everyone. So the treatment effect for the compliers is the same as for the rest of the population. So in particular, the average is also the same. Now we are in models where we allow the treatment effects to be different between people. So the late and the 8 average treatment effect, ATE, are different. And this is just how to estimate it. So you can write the model also in a form which is closer to what you saw before. And this is a form. So you can have a model yi is equal to g of zi xi plus epsilon I, di is equal to r of zi xi plus ui, and zi is equal to m of xi plus vi. And then in that model, you can essentially show that the late is given by this. I will not go into the mathematics of it, but this is just what I want you to see is more this part, that you can really rewrite the model in a standard form, right? And here you see that the effect of zi on di can be nonlinear and interactive, and the effect of zi on yi can also be nonlinear and interactive. And this is a way to estimate. So essentially, you're gonna estimate all these functions, G, R, and M by a random forest or any other machine learning algorithm on one part of the data, and on the other part, you combine it through this formula into an estimator of alpha. This complex formula, again, you should not try to, I'm not asking you to understand where the formula comes from. There is a package that will implement it for you. I'm just writing it on the slide for completeness, let's say. And then you average all the estimators of alpha. Okay. Is there any more question on this chapter? Yes, please. Yeah.
How do you formally distinguish the first and the second condition? Sorry, exogenating and exclusion.
Yeah, a lot of people are confused by this.
I understand it intuitively, but how to formally write it down.
So one way I think to more formally write it down is that in the most general world, but that's not what I think, that's not usually how people write it. But I think that so here I wrote it in the way people usually write it, but the way I would write it is the following. In the most general world, you would assume that you will define your potential outcomes as a function of d on z. Then you would say that this potential outcome for all values of d on z, so this can be 0, 1, 1, 1, 0, 0, 1, 0, they are independent of zi given xi. And this will be your exogeneity. And then you would have your exclusion that says that yi of dz does not depend on z. So I think that the most general way of writing it, so this says exogeneity is just saying once I condition on x, I fix x, di is really given randomly to people, like if it were a lottery. Zi, sorry, not di, I say zi. Di. Exogeneity is just, exclusion is just saying that z has no causal effect on yi. That's a good question. Maybe I will update the slides that way. Maybe it's better. Yes. The second one means z has no causal effect on y, because you remember this is the, let's say, the the value of yi you would observe under treatment D on IV equal to Z, and we say this value does not depend on Z. So there is no causal effect of. Is this clearer like that? Yeah, okay, then I think I will rewrite it like this. So very good point. Is there any other question on this chapter? No? So then we can have a 10 minutes break. I wait for you at 55, and then we have just a 16 slides chapter to finish. Thank you. we can start again for the last chapter, which is very short. I said it was 16 slides, it's even 15. And it's the ideas are very, very, very simple, I think, but also very powerful. And so we will talk about one of the oldest statistical methods or econometric methods, which is called difference in differences. I will explain to you what this comes to, but it's please, thank you. There is a funny anecdote here. So this method was, we know of it being first used by an English physician in the 19th century, and his name was John Snow. So for those who know Game of Thrones, it's quite ironic, let's say. And it's a very natural method to estimate causal effects. So let's take an example. We want to know what is the effect of minimum wage on employment. So this is coming from a paper of Card and Kruger in 1994, where they try to evaluate what is the effect of minimum wage on employment. Because there is a lot of political debate about minimum wage. Could it be that minimum wage decreases employment or even increases it? That's a point that some people do. And they want to evaluate that. So they had this paper, and actually Card got the same year as Imbens and Angris the Nobel Prize for Economics for this, partly for this paper. And so to do that, they consider one particular setting, which is a setting of the state of New Jersey. And in 1992, they raised the minimum wage per hour from $8.25 to $9.05. And the question is, what is the effect of on unemployment? So they do collect data on employment on 331 fast food restaurants in New Jersey. And then they can track the average employment in these restaurants before and after the reform. So just to fix ideas, this is not the real data, but let's plot the average employment. So this is time. This is 1992. Let's assume that this was the average employment before the reform. Then the reform happens. Sorry, we'll write it a bit more. Then the reform happens, and then it goes like that. Can you deduce something about the causal effect of this reform from this data? It's not so clear. You might say, look, after the reforms, employment continued to rise, so it has a positive effect on employment. But maybe without the reform, it would have continued to rise as well, right? Because if I extrapolate this trend, it would have continued to rise. But how do I know this? I don't know. Maybe there is an economic recession, maybe there are problems, and without the reform, it would not have risen, it would have decreased. That's the issue here. The issue here is that I don't observe what would have happened without the reform. So let's say, but I don't know if that is the case, let's say that this is what would have happened without the reform. If I observe this, then I could just say, okay, the effect of the reform is just this minus this. Oh, sorry, I should say the other, this minus this. That's the effect of the reform. It will be negative. Okay? But the issue is that I don't observe what would have happened. I don't know what would have happened. I don't know if the trend of before would have still been followed or if it would have changed or something like that. Okay? It could be also that what would have happened is this. Then I have a positive effect. They don't know that. That's the main issue. So essentially what you need is a control group. You need other restaurants which are not affected by the reform and which are comparable to the New Jersey restaurant in some way. And these restaurants should tell you what would have happened without the reform. So what Gardner-Kruger proposed is to use data on a neighboring state of New Jersey, which is Pennsylvania, and so they take data on 79 fast food restaurants in Pennsylvania. And what is important is that in Pennsylvania you have no minimum wage increase in 92. So they are not affected by any reform. Now you could say, okay, then I just have to look after the reform. I compare the minimum, the employment in New Jersey and in Pennsylvania, and the difference is the causal effect. What is wrong with this, you think? Yes?
You need to make sure that fast food restaurants are comparable in Pennsylvania and in New Jersey.
Exactly. So you probably have other differences than the reform between Pennsylvania and New Jersey. Because, for instance, maybe the minimum wage in Pennsylvania, even before the reform, was higher. Maybe restaurants are on average smaller in Pennsylvania because it's less dense. So you have more local restaurants which are smaller, so they have less employment. Maybe they don't, the state laws and the tax laws are different in Pennsylvania. Maybe they don't open at the same time. So if a restaurant is open longer, everything else equal, they need more employment, and these kind of things. Essentially, the data of Pennsylvania is probably looking like this. You have some data, and before the reform, the employment in Pennsylvania can be, for instance, larger than in New Jersey, because they are not fully comparable. So that's a bit the difference with before, with what we did in the previous chapter. In the previous chapter, we said once we fix X, we have a control group. We have people who are comparable. Here we don't. Here they are not comparable. So the main idea of Gardner-Kruger is to say, for Pennsylvania, I observe the data without the reform. Say it does this. I'm not going to assume that without the reform, the employment in New Jersey will be the same as in Pennsylvania. That's not realistic because before the reform, they were already different anyway. What they assume is what we call the parallel trend assumption, and that says the variation in employment in Pennsylvania after 92 is the same as the variation in employment of that New Jersey would have had after 92 if there were no reform. So I'm saying the trend of employment of Pennsylvania and New Jersey are the same. They are not equal, their employment level are not equal, but their trend are the same. So essentially the idea is to say, this is the trend of employment of Pennsylvania after the reform. I'm going to assume that without the reform, New Jersey would have had the same trend. So in other ways, I'm going to say, this is my trend. I'm going to extrapolate it here. I take it here. I put it here. And I say, this is what would have happened to New Jersey if they didn't have the reform. Okay? I extrapolate the trend here. And then I look at the difference. So this is just the same trend that I write here. It's not very parallel, so I'm just gonna try to do it again. Or this, I'm very bad at this. You will have noticed. But and then, so under this assumption, this is what would have happened in New Jersey. And so the difference between what really happens and what would have happened without the reform is the causal effect of the reform and of the minimum wage increase. Okay? So the idea is to say, I can't find a comparable control group, but I can find a group where it's somehow realistic that the variation in this control group and the variation in my treatment groups that I would have without the treatment are the same. Is this idea clear for everyone or not? Because you can essentially explain all the idea on diff with this type of graphs. Yes? Exactly. So what people do is to make sure that then Pennsylvania is a good control group, they look at the data before the reform and they check that the trends are parallel. Now there is one point which is important here. It does not guarantee you that the trends after the reform would still have been parallel. You're never sure, right? But it's a very strong suggestion. If the trends before the reforms are parallel, then it suggests very strongly that after the reform, if the reform had not happened, so after 92, if the reform had not happened, the trends would have stayed parallel. But this is not a full proof, right? It is not, but very, very good comment. And essentially, in the paper, they check this, and they see that the trend between of New Jersey and Pennsylvania before 92 are the same. Yes? Yes, so the idea, that's what we will see after, is that all this reasoning you can also do conditional on some x. Okay, and this x can be some external particular factors, but they can also be like characteristics of restaurants, for instance. And this makes this assumption more realistic, right? Like it's more realistic to say the trend is the same for let's say restaurants in rural areas than to say the trend is the same for all restaurants, right? Because it might be, for instance, that Pennsylvania's are more restaurants in rural areas, and that's why the total trend is not the same. But okay, so that's exactly the point. So this idea is a very simple form. Now we will want to control for some x, and to control for this x, again, we are going to use machine learning. Is there any other question on this? Or so you see, this is like a very intuitive and very simple technique, but it's extremely popular because of how intuitive it is. Okay, so let's try to formalize these things, this idea. So first we need to go through a bit of mathematical formalization, and then we will go to the machine learning. So essentially, you're gonna observe a panel data. So you're gonna have YIT is the employment in restaurant I at time t. To simplify, we say t can take two values. T equal 1 is before the reform, just before the reform, one measurement point just before the reform, and t equal 2 is one measurement point just after the reform. And then DIT is equal to 1 if the restaurant I at time t is affected by the reform, and 0 if the restaurant I at time t is not affected by the reform. Okay, as I said, t equal 1 is before the reform, t equal 2 is after. I simplify, I just have two periods. I have two measurement points. Yes? If you only have, well, you can look at this trend, right? Like this is, let's say this is just before the reform, and this is t equal 1, and this is t equal Of course, if you want to look at the trends before, you need more periods. But here, to simplify, we don't. But in practice, people do look at the trend before. But here, just to simplify, we have only two periods. Okay, so t equal 1. That's a good point. T equal 1 will be here. That will be the first measurement point just before the reform, and then this is t equal 2. And of course, if you want to look at the trend before and indeed check if they are the same, then you need more period. And so here what will happen is that for restaurant in Pennsylvania, there is never a reform, so DIT is always equal to 0. For restaurants in New Jersey, then DI1 is equal to 0, and DI2 is equal to 1. So period 1 is just before the reform, period 2 is just after. Or just after, or sometime after. Is this framework clear for everyone? Okay, thanks. So here we can define. So YIT0 is then the employment that restaurant I, we can define the potential outcome, sorry, employment that restaurant I would have had at time t if the minimum wage was set to its value at the beginning of 92, so before the reform. If the reform did not, if there was no reform, if the minimum wage didn't change. YIT1 is the employment of the restaurant I would have had at time t if the minimum wage was set $0.8 higher than at the beginning of 92. So if the reform had happened, if they are affected by the minimum wage rise. And what we observe is YIT of DIT. So we observe the employment corresponding to the actual value of the treatment, which is always 0 in Pennsylvania and 0 and then 1 in New Jersey. Is the formalism clear for everyone? Okay. And so what we will be able to identify by this, you saw here the logic. We want to identify the effect on New Jersey of the minimum wage. We extrapolate what would have happened using Pennsylvania. So here we are interested in what we call the average treatment effect on the treated. So why on the treated? Because here we have the effect on New Jersey, and New Jersey are the people who are treated. Like the restaurants in New Jersey are the ones who are treated. So this is it. So you have the average of YI21 minus YI20, so that the employment in period 2, so after the in the period after the reform, that restaurant I would have had if the reform happened minus what they would have had if the reform did not happen, and we average over DI2 equal 1, meaning we average over New Jersey, over restaurants in New Jersey. So this is just a slide that talks about what I told you earlier. Like what you might want to do is just to say, and we know that's wrong, is just to say I compare this point to this point. So I compare the employment in New Jersey after the reform to the employment in Pennsylvania. That this is the average employment in New Jersey in period 2 and the average employment in Pennsylvania in period 1. And we said that doesn't work because they are not comparable control group. Because there are many reasons why the employment in Pennsylvania and New Jersey are different, except and only the reform. That's what we said, so that's why we have to use the trend rather than the level itself. So the more credible approach is diff in diff. That's the one where we extrapolate the trend. So what do? We compare the variation in New Jersey, the time variation in New Jersey to the time variation in Pennsylvania. And that's exactly what we were saying here. We are saying, so this is what happened in New Jersey, and we say what would have happened without the reform in terms of variation of employment is the same as in Pennsylvania. So to get the causal effect, you need to see the variation that you really saw in New Jersey minus the variation in Pennsylvania, which would be, under our assumption, the variation that would have happened in New Jersey without the reform. So that's what the diff in diff does. It's using this trend here to extrapolate the trend in New Jersey, and it's called difference in differences because you have a first difference here, you have a second difference, and you do the difference of these two differences. Okay, so the first one, this is just the difference in employment before, after 92 and before 92 in New Jersey, and this is the one in Pennsylvania, right? So the first difference is this point minus this, and the second is this point minus this. Okay? That is just the time variation. Is this formula clear for everyone, or is there a question? Yeah? On the graph, yeah. So this first thing here is the average employment in New Jersey after the reform. So it corresponds to this point, this value. Then this is the average employment in New Jersey before the reform, so it corresponds to this point. So in a sense, if you want to compute that, you just take this like horizontally, you go here, and you take this minus this. And here this is the employment in Pennsylvania after the reform, so it's this point. I can remove this for now. And this is the employment in Pennsylvania before the reform. So it's this point. So if you want to compute that, you just take this horizontally, you arrive here, and you do this minus this. Okay? So that's how it varies over time in both cases. And as we said, the underlying assumption is this parallel trend, that the trend of employment in New Jersey would have been the same as in Pennsylvania if there was no reform. So this is just another graph to explain this. So this will be here, not the same graph as here. This will be New Jersey. So it starts like this before the reform, and then after the reform, that's what you observe in terms of employment. And what we are assuming is that this is the employment in Pennsylvania. We are assuming that what would have happened in terms of trend is in New Jersey is the same as in Pennsylvania. So the orange is what would have happened without the reform, and then if we take the difference, we get the causal effect. Okay, this is just another graph to show this. But I prefer my graph because not everything is parallel, which is good. Okay, and so this is the main assumption, it's a parallel trend. So the average variation in employment in the case where you have no reform between period 2 and 1 is the same in Pennsylvania and New Jersey, right? When you condition on DI2 is equal to 0, that means you are in Pennsylvania, because these are the ones who never have the reform, so they have DI1 is equal to DI2 is equal to 0. And when you condition on DI2 is equal to 1, then you are in New Jersey. Okay, so this says exactly the same. This is the trend in employment that you would have had in New Jersey without the reform, and this is the trend of in employment in Pennsylvania. So this is the assumption, the parallel trend assumption. Average, I should say average, trend in average employment, because these are average. And as you said, we can always check if it holds before the intervention. You can always check if before the intervention, the trends are really parallel. And if they are, it's extremely subjective that they would have been after the intervention in the absence of the intervention itself. So these are the figures, by the way, in this example on New Jersey and Pennsylvania. So at the time, this was almost a revolution, because what you see is So before the 92, this is the average employment in New Jersey, and then it increases to 0.47 in between before and after the reform. In the meantime, employment decreases in Pennsylvania from 23.38 to 21.10. So what the definitive assumes is if there was no reform in New Jersey, the employment would have varied in the same way as Pennsylvania, so the employment would have decreased by 2.28 people, full-time equivalent people. But in practice, because of with the reform, it increased by 0.47. So the effect of the reform is the difference between these two. So it's 0.47 minus 2.28, and so it's 2.25. Okay, without the reform, that's what we see here. Without the reform, employment would have decreased by 2.28, but actually, in the world with the reform, it decreases a bit by 0.47, and the difference between the two is 2.75, and that's what we have as a causal effect. So this paper was huge because people believed the identification of the causal effect, because you would see, I mean, you may not believe in the parallel trend, but you will actually see that the trends were parallel before the reform. So that was extremely suggestive that this is a correct identification strategy for the causal effect. And at the same time, the result is very surprising because most economists were expecting that raising the minimum wage would decrease employment. And actually here you see that it increases employment. And the rationale for this is, in particular in that case, this is employment in fast food restaurants. People who tend to go to fast food restaurants tend to be working class people. So when you raise the minimum wage in your state, these people have more money and they tend to go to the restaurant more. And so you have more demand, so they employ more, essentially. And of course, you have an effect that it's a bit more expensive to employ, but let's say the demand effect dominates this effect of the fact that it's more expensive. Now, just a digression, the main consensus of economists nowadays, of the literature, is to say that minimum wage has very little effect on employment across many settings. Some say there is no effect, some say there is a little positive or little negative effect. But the main consensus is that there is very little effect on employment or minimum wage, at least in the short term, because this is the short-term effect. Okay, is that clear so far? Yeah. Yeah, exactly. So, but here it holds actually non-conditionally in that example, but that's what we will see just after. That, of course, asking it to hold conditionally on some x is more realistic. As I said, it's more realistic that it holds conditional on being a rural restaurant or a city restaurant than in general without conditioning. So that's exactly the next slide. So you can consider difference in differences with covariates. Then, if you control on covariates, you can do that controlling on covariates. So you could reproduce this graph for, say, rural restaurants and urban restaurants. Do the same thing, and then you get an effect for rural restaurants and urban restaurants. And if you want, you can average this to get an average effect over all the restaurants. So this is more realistic. And so in that case, you just need a parallel trend conditional on covariates. So once you've fixed the covariates, you've said these are urban restaurants, for instance, or these are restaurants which are open up to 11 p.m., for instance, then you assume that they have the same trends. And that makes it more realistic. And now you have all this question of how can you control efficiently for these covariates? Because this creates problem when you have covariates, like you need to control for them. It's a non-parametric problem in a sense, Because if your covariate says are something which is a bit more granular, so it could be, for instance, the opening time. You may not have many restaurants to compare to each other, right? You might you have very few restaurants with the same opening times between the two, so you need to use machine learning to find good comparison groups. So here are an example of a covariate that's also the same, like the number of hours a day a restaurant is open. And why would it be important to control for such a covariate? Well, it could be that people there might be evolving preferences of consumers over time. So it could be, for instance, that over time, consumers prefer more and more to eat late. Okay, if that is the case, then if New Jersey has more restaurants open late at night than in Pennsylvania, then you would expect that the trends are not parallel between the two, right? Because employment will increase more in New Jersey because people like to eat late, and there are more opportunities to eat late in New Jersey. But now, if you control for this, if you just control for the number of hours, then between restaurants in Pennsylvania and New Jersey, which have the same number of hours where they are open, the trends can still be parallel. Okay, this is just one example. So now, how do we perform double machine learning here? How do we control for these covariates, essentially? Okay, because there is always this question, the number of hours that you are opened is mainly a continuous variable, because you can also be opened, let's say, a half hour or a quarter or something like that. And you need to control for this in a good way, right? Because if you just do it naively, I just compare restaurants open 8 hours a day to restaurants open 8 hours a day, then you have very few restaurants each time. Okay, so you want to use more a machine learning technique to kind of find the right way to do that. And so very similar to what we did with the interactive regression model, we are going to have to estimate two quantities. One is what we call the propensity score last time, so that's the probability given X to be treated. So that tells you the proportion of for a given value of X, so let's say among the restaurants which are open 8 hours a day, this is the proportion of those who are in New Jersey in your data. And this is just the time variation in outcome in the control group with xi is equal to x. So this is just in Pennsylvania, for restaurants such that xi is equal to x, what is the average variation in employment? Okay, so if x is 8 hours, this is the average variation in employment among the restaurants opened 8 hours in Pennsylvania. Both of these functions you can try to estimate with a random forest. Okay, and the random forest will decide for you, do I just average on the restaurants which are open 8 hours, or do I also average with the restaurants which are open 7 hours and 30 minutes and 8 hours and 30 minutes, and it goes on. And this is the general algorithm to use machine learning with for difference in differences. So you will again do this cross-fitting. You divide your data in fold. For a given fold, you take the data not belonging to this fold, only to estimate M and G. And you also need to estimate just one more thing, which is this you don't need to estimate it by machine learning, which is just the probability of being treated. So it's just the proportion of treated in your data on this fold. And then you combine everything on the rest of the data you haven't used to train, through this formula. Again, you don't have to understand where the formula comes from. You don't have to know it as well. It's just there for completeness. You do that for every fold, and you average the estimators. Okay, so this is how you can use machine learning to do definitive with covariates. And if you want more info on this, you can look at this chapter of the COSA ML book. Is there a question on this first? Yes.
I have a question about the notation on slide 9.
9. Yes.
I don't really understand that the dy is 1 and then 0.
Okay. So yeah. So dy2 is the treatment state of restaurant I in period 2. So after 92.
Is it, maybe I didn't understand that. Isn't the 0 in the brackets also about the d? No.
Here you mean? Yes.
No, before, like ey2 0.
This is because it's a potential outcome. So you remember we have these potential outcomes, yit d. So yit0 is just the employment in restaurant I at time t if they are not affected by the minimum wage increase.
But depending on that they are affected. Or
Well, on the left-hand side, I take the average over the restaurants which are affected by the reform. So this average, I can never observe it really, right? Because for the restaurants which are affected by the reform, I will never observe yi21 at yi20, right? That's what you're saying. So this average on the left, I can never observe it. The one on the right, I can observe, right? Because for restaurants which are not affected in period 2 at the reform, they are never actually affected by the reform, right? So yi20 is just their yi2, and yi21 is just their yi1.
so the left side is the effect of the restaurants in New Jersey who are affected by the reform as if they were not affected.
Exactly, but this I can't observe, but I'm assuming it's equal to something on the right, which I can observe. So that's all I extrapolate it in a sense. I use something that I can observe and I assume it's equal to it. Is that clear or are there other questions? Yes?
Like, can you also use something like this if you have like staggered adoptions?
Yes, so there are variations with staggered adoption. So what you mean by staggered adoption is saying yeah, the treatment is not given at the same period. So let's say you have many states and they raise minimum wage at different times. So there are adaptations of this for staggered adoption, let's say, but essentially the main idea that is one of the main ideas that when you have staggered adoption, you can always look at your data and just define these 2 periods by 2 periods, and for these 2 periods, it's a standard diff in diff. And then you do that for the standard diff in diff, and then you average over the periods in one way or another. So you can generalize this. I don't go into it, but you can do that for staggered adoption as well. You're welcome. So, is there any other question? Yes.
If your parallel trends are valid even when not conditioning on a certain x,
Yes.
can you make a stronger conclusion than if you were to condition on x?
That's a good question. I mean, one thing that the thing is the following: is conditioning on X can still give you more information, because then you can also obtain average treatment effect on the treated conditional on X. So you can see if the effect is different for restaurants which are open 10 hours a day and for restaurants which are open 6 hours a day. So in a sense, you get more information by conditioning on X, although you have to be careful that hypothesis testing becomes complex. Like this technique here is really, you condition on X, but you try to estimate the average effect of everyone. not an effect conditional on X. That's important. But so this gives you a bit more information. Otherwise, my view, but that's is that if both conditioning on X and not conditioning on X, I cannot reject parallel trans. I see parallel trans. That makes me even more confident that it's correct. But in terms of identifying the overall effect, it doesn't change anything. You can use one or the other to identify, but it will make me more confident at least, right? That it's the case. Because these are all statistical techniques. So you're gonna do a statistical test, and let's say you don't reject parallel trans, let's say unconditional on X. If I only have this, my test can be wrong by definition of the test. If I don't reject, that doesn't mean I'm 100% sure that there is parallel trans. It just means I have very high likelihood of having it. Now, if I don't reject as well when I condition on X, that makes me more confident. So I hope that answers your question. Are there other questions? So then I just want to finish by saying one important remark about these techniques. So this DFINDIF, for instance, has gained a lot in popularity in the past 10 years. And people have talked about that as what they call the credibility revolution in economics or in econometrics. And I think that's important to know. And why do they call that a credibility revolution? Because in all the previous chapters, we were making this exogeneity assumption, but we have no way to check it, right? We are just hoping that by adding more X, we make it more likely, but we have no way to check it. Here you have a very convincing way to check the assumption is to check this parallel trend before the reform. And again, that's not 100% correct. Even if it holds before the reform, you never know what would have happened after, but it's extremely suggestive. This is much more, let's say, convincing to people that just standard techniques based on exogeneity without panel data. So, and here it's really the time variation having a long panel that allows us to check our assumption, which we can't do with just one cross-section, with one snapshot in time. So that's why more and more economic and econometric research has focused on this kind of settings where you have panel data, where you observe things over time, because that makes the finding much more credible. Okay, so that was the main point I want to do. Sometimes you can't observe things over time. Sometimes it can be very hard, but sometimes you can. And when you can, when you have a data set where you observe people over time, you should leverage it and use this kind of techniques. When you can't, you can use the techniques we studied before in the course. And you can always implement machine learning for this kind of techniques as we saw. Yeah. Is there any other question on this? And is there also any other question on the course? Otherwise, I'll thank you for coming to the lecture. So next week there is nothing because it's a day off. And the week after there will be the last tutorial where you will study the late, like all this, the interactive IV model and the DFINDIF. And then there is a Q&A in June and then the exam. So good luck for the preparation. You can send us email, we reply quickly. So no worries, you can send any question you might have by email. Thank you. Thank you. Yes. No worries, no worries.